All right. So although we've already learned about torque, we don't quite have the whole story yet. The formula we have for torque is this guy. Torque is force times distance, and they have to be perpendicular. So we've only seen torque provided by forces acting perpendicular to the body in equilibrium. Every question we've sort of looked at so far, there's been a force, and it's acted at a distance and from a pivot point, and we've just had to double check that that force is perpendicular to the distance from the pivot point. And every single time, it has been perpendicular. So that sort of reminder about being perpendicular is something we've always checked, but we've never found it to be not the case. In today's lesson, we're going to look at situations where the force is not perpendicular to its distance from the pivot point. And let's start this by doing an example. So a 2.2 meter long, 50 Newton uniform beam is attached to a wall by means of a hinge. Attached to the other end of the beam is a 100 Newton weight, and a rope also helps support the beam as shown. What is the tension in the rope, and what are the vertical and horizontal components of the supporting force provided by the hinge? Okay, so let's forget the fact that I said there's something new going on in this problem, and let's just set it up like we would set up any regular torque problem. We're going to start with a free body diagram. As always, we want to pick one object for our free body diagram, and it's wise to pick an object that's in equilibrium and has all the forces acting on it. So I think that object is going to be this beam itself. So drawing a free body diagram for that beam might look something like this. I have the weight of the beam itself acting in the middle, 50 newtons. I've got the weight hanging on the end of the beam. That's 100 newtons. I've got this rope acting up at an angle. We'll call that a tension force, Ft. And then I've got some sort of reaction forces at this hinge over here. Remember, a hinge is capable of pushing or pulling in any direction. So it can push or pull left, right. It can push or pull up, down. Now, one little extra thing I want to throw in this problem is I want to show you what would happen if we assumed the wrong direction for this hinge. So I think from looking at this scenario, if this hinge were to suddenly disappear, probably this beam here would move to the right and down. So that makes me think that because it's not moving to the right and down, the hinge is probably pulling it left and up. So over here on my free body diagram, I draw force going to the left, and I call that the hinge force in the x direction, and I draw force going up, and I call that the hinge force in the y direction. But just to kind of illustrate a point, I want to show you what would happen if we got the direction wrong at this point in the problem. Let's say it wasn't that obvious to you that the hinge was pulling up and you thought maybe this hinge was actually pushing down. So then instead of writing the y force of the hinge like we did, you might write it like this. Hinge force in the y direction. And the only reason I've done that in red is just to remind us that this is actually the wrong direction. So we're going to look at it later, but it's okay that we've assumed the wrong direction. The problem's sort of going to fix itself later on. That was just a sort of a side point I wanted to make here. It's not the main part of this problem. So next thing I'm going to want to do is pick a point to act as my pivot. In this question, there's a fairly obvious pivot point. It's the hinge, so we might as well pick that. So in my free body diagram, I'm going to mark the location of the hinge as my pivot point. And now we're looking at how we're going to calculate some torques. So I have my hinge forces, which go directly through the hinge themselves. So the distance from the hinge for those forces is 0, so they won't create any torque. I have this force, which is perpendicular to its distance from the hinge. I have this force, which is perpendicular to its distance from the hinge. And then I have my tension force. And here's where things get different. This force is not perpendicular to the distance from the hinge to where it acts. So what are we going to do about that? Well, since the tension is not perpendicular to R, we'll break it into components that are perpendicular and parallel. To R. So let's see what that looks like. That'll look like one component like this. That's perpendicular to R. And one component like this. And that one is parallel to R. So although FT was at a weird angle to the distance from the pivot, this component is nice and perpendicular to the distance, and this component is totally parallel to the distance from the pivot. And let's note that what we know about parallel forces, forces that are parallel to the distance from the pivot, is they create no torque. So when I look at forces that are actually going to create torques here, this guy will create a torque, this guy will create a torque, and this guy will create a torque. This guy creates no torque because it's parallel to the distance from the pivot, and these guys create no torque because they go through the pivot themselves. So it's just those three forces highlighted in yellow that I have to worry about. Now, one thing I want to point out is when we have this situation, right, where we had this force, Ft, that wasn't perpendicular to its distance from the hinge, we want to split it into components that are perpendicular and parallel to R. Now, in this particular situation, that meant having one component that was in the vertical direction and one that was horizontal. That seems very familiar. We're very used to breaking things into X and Y components, but it doesn't have to be X and Y components. In this situation, yes, it ended up being a Y component and an X component, but only because the Y direction was perpendicular to the distance from the pivot. That's the thing we need to have. We need this component to be perpendicular to the distance from the pivot. If that happens to make it in the Y direction or the X direction, that's fine, but we don't need them to be X and Y. We need them to be perpendicular and parallel to R, the distance from the pivot. Okay, so now let's start to solve this, just like we would any other torque problem. We know this scenario is in equilibrium. So the sum of all the torques will be equal to 0. So remember, it's just these three vectors here that create torque. So those are the three I'm going to put in my torque equation. So I've got 50 newtons. And that's being multiplied by a distance of Well, let's see what we're given here. We're told that the beam is 2.2 meters long. So that whole thing is 2.2. So that means that from here to here is going to be 1.1. I might just add that to my free body diagram. Okay, so I have 50 newtons, and that's acting at a distance of 1.1 meters, and those are perpendicular, so that's great. And this 50 newtons is trying to rotate my beam about that pivot point in a clockwise direction, so that's going to be a negative torque. Next up, I've got my 100 newtons. That's also going to try and rotate the beam in a clockwise direction. So that'll be a negative torque. And it's at a distance of 2.2 meters. And then I've got this guy here. So that, if we do a little bit of geometry here, we know this angle up in the top is going to be 30 degrees, because that should match with this angle we have over here. So this perpendicular component is going to be Ft times the sine of 30 degrees. So my force is going to be, and this guy is going to try to rotate things in this direction, the counterclockwise direction, making it a positive torque. So a positive torque that comes from the force Ft sine 30 being multiplied by a distance of 2.2 meters. Okay. So that is the sum of all my torques acting on this beam about that pivot point. And because it's in equilibrium, that needs to equal 0. So let's go through and see if we can solve this. Ft is the only thing in this equation I don't know, so I should be able to isolate Ft and get Ft equals 50 times 1.1 plus 100 times 2.2 divided by 2.2 times sine 30. What I've done there is I originally kept this stuff on this side of the equal sign, and I moved these two terms to the other side. And then after I did that, to get Ft all by itself, I divided both sides by sine 30 and by 2.2. And I don't know why I threw that m in here. For, for meters, I don't normally put units in formulas. Okay, so if we solve this, we should get that Ft equals exactly 250 newtons. Okay, so I think that solves part A, what is the tension in the rope. Part B means we need to know the vertical and horizontal components of the supporting force provided by the hinge. In other words, we need to know this guy and this guy. So I think to find those, there are a few ways we could go about this. I think the easiest way is to, now that we've already looked at the torques, let's look at the forces, specifically in the x direction and the y direction. So because this beam is in equilibrium, not only does there need to be no net torque, but there needs to be no net force. So we need to have no net force in the x direction and no net force in the y direction. Just going to move this over a little bit to give myself some more space. Okay, so if I say the sum of all the forces in the x direction equals 0, that means, well, I only have two forces in the x direction. I have hx, which is moving in the negative direction, and I have this guy, which is going to be ft cos 30, and that's in the positive direction. So I'll label this here, ft cos 30 degrees. So in the x direction, I have negative hx plus ft cos 30 equals 0. So that tells me, if I rearrange this, that hx equals ft cos 30. We could probably see that graphically. Since I've only got two forces, one's pulling left, one's pulling right. If it's in equilibrium, those forces need to be equal to each other. So ft is 250, because we just solved for that over here. Which means that hx is going to be 217 newtons if we round to 3 sig figs. Now let's look at the y direction. So the sum of the forces in the y direction also has to be 0. These are basically our equilibrium conditions. This and this tell me it's in translational equilibrium, and this tells me it's in rotational equilibrium. So by using all three, I've used the fact that I know this is in complete equilibrium, both translational and rotational. Okay, so in the y direction, I have my hy, which is going down, my 50 and my 100, which are going down, and my ft sine 30, which is going up. So 3 negatives and 1 positive. So negative hy minus 50 minus 100 plus ft sine 30 equals 0. Okay, I'm going to help solve for hy by moving it to the other side, so it'll become positive. And that'll give me hy equals ft sine 30 minus 100 minus 50. And because I know ft is 250, I can plug that in. And that tells me hy is equal to negative 25. Okay, now that's odd. Remember, hy is the magnitude of the force. I should, actually, to remind myself, I should probably put vector hats on my original equations. The forces in the x direction are vectors. They have direction and magnitude. The forces in the y direction are vectors. They have direction and magnitude. So when I put vectors in, for hy, for example, this minus was the direction and hy was the magnitude. So when I solved for the magnitude, I got a negative number. And that makes no sense. A force can't have a negative magnitude. It can be going in a negative direction, but a negative magnitude makes no sense. So if you're solving for the magnitude of a force and you get a negative number, it tells you something's up. And what that tells you in this case is that you assumed the wrong direction. The direction is actually opposite to what you assumed. And you might remember we assumed at the beginning that hy was moving down, and we sort of suspected that that was a wrong assumption. So this tells us that yes, that was the wrong assumption. If it was going down, it would have to have a negative magnitude, which makes no sense. Therefore, it needs to actually be going up. So a vector that's going down and has a magnitude of negative 25 is really a vector that's going up that has a magnitude of positive 25. So the proper way to write this would be the hinge force in the y direction is 25 newtons, and we assumed it was down, but we got a negative number, which means it's actually up. So 25 newtons up. And that actually reminds me we should probably have done that with the x force too. In the x direction, we assumed it was going left, and we got a positive number. So that means we assumed right, and it is in fact going left. Okay, so there, I think we've solved this whole problem. So let's just recap. This looked not unlike a problem we'd had before. The only thing that was a bit odd was this one force was not perpendicular to the distance from where it acted to our pivot point. And we dealt with that the same way we always deal with forces that are in directions we don't like. We split it into components that were in directions we do like. One component that was perpendicular to the distance, and then one component that was parallel to the distance. Then we just continued on, basically forgetting about the original force, and instead using these two components. We used our equilibrium conditions, one at a time, and just plugged things in to those equations until we were able to find all the stuff we needed. And we did have one little scenario where we got a negative number for the magnitude of a force. And that just meant, it told us that the direction we had assumed for that force must have been wrong, and that it actually must be going in the opposite direction we'd assumed. So because we assumed it was going down, we now know that it must have actually been going up. So the key point here that's new to this lesson is that when we are calculating torque, we must use the component of the force that's perpendicular to the distance, which is exactly what our torque formula tells us. When we're calculating torque, we have to use a force that's perpendicular to the distance from the hinge. Let's move on and look at another example now. Okay, so here we have another beam, a uniform beam, supported by a hinge attached to a wall. We've got a mast hanging from it and a rope supporting it. Pretty simple, pretty common scenario. We're seeing just the angles are a little bit different in this scenario from what we're maybe used to. So let's start with a good free body diagram. Okay, there is my beam. So we've got the weight of the beam is 115 newtons. So that will be acting right in the middle of the beam. And I'm thinking I might just make this diagram a little bit bigger because I know I'm going to have a lot of triangles here. So bear with me for a second. Okay. Then I also have this mass hanging from the edge of the beam. Don't know exactly what it is, but there's an FG hanging down there. And I've got a tension pulling the end of the beam in this way. We'll call that FT. Oh, and we actually know that it's 675 newtons. So let's just toss that right in there. And at the hinge, okay, let's see if we can just guess and find these reaction forces right. The first time, okay, looking at this hinge, I think if this hinge were to just dissolve and completely disappear instantly, I think that the end of this beam would probably move down, and I think it would move to the right a little bit. So that tells me the hinge is probably pushing, it's stopping that from happening, so it's pushing left and up. So we can draw some hinge forces here, one reacting left and one reacting up. HX and HY. Now, we don't need to worry about that too much. A, because if we assume the wrong direction, we'll just get a negative number for the magnitude and be able to fix it right away. And two, because I don't think we're going to actually use either of these forces in this problem, because I think we're going to use this as our pivot point, and so both of those will create no torques. And I think the torque formula is the only one we need to use in this question. But let's see. Okay, so as I was suggesting, let's pick this as our pivot point. And now let's look at our forces. So probably I will measure all these forces are acting at points on the beam. So I'll probably measure my distance along the beam. I'll measure my distance from here to here for the first torque and all the way up to here for these next two forces or torques. So I need to have forces that are perpendicular to that distance if I want to know what torques they create. And none of those forces are perpendicular to that distance. So I'm going to have to break them all into components. Let's start with this 115 newtons. I'm going to break this into one component that is perpendicular to that distance, perpendicular to the beam, and one component that is parallel to the beam. And then I'm going to do the same up here with my FG. One component that is perpendicular to the beam, and one component that is parallel to the beam. And again, with my 675 newtons, one component that is perpendicular to the beam and one component that is parallel to the beam. Remember, I said on this last page that when we do these components, sometimes they end up being in the horizontal and vertical directions, but they don't have to be. What's important is that they're parallel and perpendicular to the distance from the pivot. And that's what we have here. Here's my distance from the pivot, and here's my components that are perpendicular to it, and here are my components that are parallel to it. You'll notice none of these components are in the X or Y directions. That's not what's important. What's important is that they're parallel and perpendicular to the distance from the pivot. So let's see if we can say what some of these forces are. Okay, so we know this angle here is 50 degrees. So by the Z rule, I have kind of the letter Z here. Remember, the two angles in a Z need to be the same. So that means that this angle here is 50 degrees. And then since this is a 90-degree angle, if this guy is 50, then this guy needs to add to that to be 90, so that little guy is going to have to be 40. Well, let's add that in here. This guy is 40 degrees. And we can do the same thing for this next torque, or next force. Again, we have a Z scenario here. So those two angles need to be the same, which means this guy has to be 50. And then since I've got a 90-degree angle here, that makes this guy 40. And then how about up here for this top one? Well, I can kind of imagine a bit of a right-angled triangle forming here. There's a right-angled triangle, sort of an imaginary one. So that means these two angles need to add to 90, making this top one 40 degrees. So it can add to this 50 to get 90. So if that guy here is 40 degrees, then this guy has to be 50, because those two have to add together to get 90 degrees. So let's add that in. This guy is going to be 50 degrees. Okay, now let's try and write what some of these components are actually going to be. Let's try and write out their magnitudes. And to save us a bit of work, I'm not going to write out the magnitudes of the parallel components, because I know that those parallel components won't create any torque. So they're not going to appear in my torque formula. So I don't need expressions for them. Let's just do the perpendicular ones. So this is going to be 115 cos 40. This guy over here is going to be FG cos 40. And this guy is going to be 675 cos 50. Okay. So I'm done my free body diagram. I've split all the necessary forces into components that are perpendicular and parallel to the distance from the hinge. Now let's do some math. Let's get out my equilibrium condition. So I know the sum of all the torques has to be equal to 0. So torques are force times distance. So let's just kind of go through these guys one at a time. Let's look at this force here. It's just the perpendicular ones, remember, and multiply it by that distance there to get my first torque. Well, right away I have an issue, and that's that I don't know that distance. So that's okay. I'm just going to call it x. So we'll say the distance from here to here is x. So that torque is going to be 115 cos 40 times a distance of x. And that is going to try to spin me. If I'm spinning about this point, this guy's going to try and spin me in this direction. So counterclockwise, meaning this guy is going to be a positive torque. Next up, look at this guy and the torques they create. So I've got another positive torque from Fg cos 40. And that's going to be at a distance of 2x from my rotation point. And then I've got a negative torque from 675 cos 50 and that's also at a distance of 2x from my rotation point. And those are all the forces that'll create any torque. Remember, these original forces I'm not looking at anymore because I'm looking at their components instead. That's what components allows us to do. These components I'm not worrying about because they are parallel to the distance from the hinge, so they do not create any torque. And these forces down here I'm not worried about because they act at the rotation point. So the distance from them to the rotation point is 0, so they'll also create no torque. So it's just the 3 I've written down that I have to worry about, and those are going to add to 0. So now we can deal with this x. The nice thing here is because I have an x in every single term, I can just divide my whole formula, my whole equation, both sides, by x. I can divide this by x, and it'll go away. I can divide this by x. It'll go away. If I divide this by x, it'll go away. And if I divide this by x, it still stays as 0. So by dividing both sides of my equation, every term by x, they all cancel out. So then I can rewrite this and solve for Fg. I'll do this in one step. So this negative 675 cos 50 times 2, I'm going to move that to the other side. Then I'll move my 115 cos 40 to the other side. And then I'll divide by cos 40 times 2 to get Fg all by itself. So that gives me Fg is equal to 508.89. That's newtons. I'm keeping that to 5 sig figs because I'm not quite done yet, because what this question was actually asking me for was the mass. I have found Fg, the weight, so I need to do one quick last conversion, and that's because Fg equals m times g. I can get m is Fg over g. So 508.89 divided by 9.8, giving me 51.9. Okay, so quick recap. We drew a free body diagram. Any forces that weren't perpendicular to the distance from the hinge, we split into components. So we had a perpendicular component for all of those forces. Then there was a length we weren't sure about, so we just called it x and sort of crossed our fingers. We used our equilibrium condition, that the sum of the torques is equal to 0. And we got lucky and found out that indeed our x, our unknown length, did completely cancel out across the board. We were able to solve, and we found the mass. At this point, I want to just show you one other thing to think about. And this is sort of a bit of an extension. You can, if you want, you can turn the video off at this point. What I'm about to say, you don't need to know. There's no problem I will ever give you where you need to know this bit. But it is sort of an interesting theoretical point, and it might help you in some situations. So let's write this down here. This is an optional point. So our formula for torque says torque is force times distance, and they have to be perpendicular. And what we've been doing in this lesson is we've looked at what the distance is, and if our force isn't perpendicular, then we break the force into components. So the distance we measured as we always would, and we broke the force into components. However, there's nothing in this formula that says the distance has to be kept as is. It just says whatever distance you use and whatever force you use, they have to be perpendicular. So rather than keeping the distance and splitting the force into components, we could keep the force the same and split the distance into components. Let me show you what that would look like in this example we were just looking at. And let's just take this very first force here, the 115 newtons at a distance of x from the hinge. Let's redraw that and show what this diagram might look like if we split the distance into components instead of the force. So here's my 115 newtons. Here's my rotation point, and my distance is x. So, again, what we did last time is we said we want to keep this distance as it is, and we want forces that are perpendicular to it. So we took the 115 and we created one component that was like this and one component that was like this. But what we could have done instead is kept the force as it is and split the distance into components. We would want one component that is perpendicular to the force and one component that is parallel to the force. So let's see what we have for angles. We said that this angle up here was 50 degrees. So since I got a 90-degree angle here, my angle on the bottom should be 40 degrees. So this is 40 degrees. And this would be x cos 40 degrees. So what I could do when calculating the torque about this point created by this force is I could keep the force as it is, 115, and I could multiply it by the component of the distance that's perpendicular to that force. Here's my force. Here's the part of my distance that's perpendicular to it. So I would get 115 times x times cos 40. Now what we did up here is we had 115 times x times cos 40. That's the exact same thing, only we got it two different ways. Here, it was 115 times x cos 40. We split the distance, into components. And up here, it was 115 cos 40, because we split the force into components, times x. So we got the exact same result two different ways. One by splitting my force into components, and another one by splitting my distance into components. It doesn't matter which way you do it, as long as you end up with a force and a distance that are perpendicular to each other. Okay, so instead of using the distance as is and splitting the force into components, you're welcome, if you want, to use the force as it is and split the distance into components. And as we've just seen, that gives us the exact same result, regardless of which way we do it. Again, this whole thing is optional. You can ignore this whole section and just go about splitting forces into components as we've always done, and you'll never run into any issues.